When a single positive charge is in the presence of another single positive charge, Q1 and Q2 are separated by a distance of r, then I know that charge number 1 is able to repel charge number 2 with some amount of force. By Newton's third law, we could say charge number 2 is repelling charge number 1 with that same amount of force. But in terms of calculating that force, I haven't quite made up my mind exactly how this works. I think it might be the case that charge Q number 1 is the one that's creating the electric field. So Q1 has an electric field that points radially outward in all directions. And so Q2 is sitting in the field created by Q number 1. So at a distance of r from Q number 1, we would have a field strength equal to 1 over 4 pi epsilon naught times Q number 1 divided by r squared. So then the force experienced by charge number 2 would be equal to charge number 2 times the electric field made by charge number 1, and this would come out to 1 over 4 pi epsilon naught times Q2 times Q1 over r squared. But after some more thought, I realized I might have it wrong. It might be the case that charge 2 is the one that's creating the field. And so it has field lines pointing radially outward in all directions. And here at some distance of r away from charge Q2 is an electric field equal to 1 over 4 pi epsilon naught times Q number 2 over r squared. And so once I place positive charge Q1 at that position, now it experiences a force, and this force experienced by charge number 1 would be charge 1 multiplied by the field created by charge number 2. But you can see this actually just gives the same result, doesn't it? 1 over 4 pi epsilon naught Q1 times Q2 over r squared versus 1 over 4 pi epsilon naught Q2 Q1 over r squared. Well, there's no difference between the numerators in these two equations. So really it is a mutual force of repulsion when you have two like charges, and a mutual force of attraction if it were two opposite charges. What does this have to do with magnetism? Well, I'm interested in figuring out what would happen if I took a wire and ran a current in this direction through that wire. I know that that's going to create magnetic field lines, and the magnetic field lines go in circular paths around the wire. Now, what's the direction of this? At points below the wire, if we were to draw this again, when current flows to the right, magnetic field lines point into the page, down below the wire, and point out of the page, up above the wire. So here's what I'm getting at. If I take a second wire and place it in the field created by the first wire, will these two wires exert a force on one another? So if I have current number 1 flowing to the right in wire number 1, and then I have a second current, number 2, flowing to the right in this other wire, do the two wires do anything at all? Do they attract each other? Do they repel each other? Well, the way we've drawn this, we're suggesting that it's the current in wire number 1 that's creating this field that's all around it, and it's wire number 2 that's been placed within this field created by wire number 1. And you should recall that the magnetic field at a distance of r away from any wire is equal to mu naught I over 2 pi r. So we can say this is the magnetic field number 1 due to current number 1 flowing in this wire. So then we go back to the equations we know for force on a current carrying wire. The amount of force on a wire in a magnetic field is just equal to the field that it sits in times the amount of current times its length. So if these two wires are of the same length that we call L, then the force on wire number 2 is the magnetic field created by wire number 1 interacting with the current flowing in wire number 2. So we can say the force per unit length, if we divide both sides of the equation by L, is equal to mu naught I1 over 2 pi r. That's the magnetic field created by wire number 1, and then I have to multiply that times current number 2. So we can say force per unit length for two parallel wires is equal to mu naught I1 I2 over 2 pi r. So this is an inverse law, but it's not an inverse squared law. This is r to the first power. Perhaps we have this all wrong. Maybe it's the current that's flowing in wire number 2 that's creating the magnetic field. So the magnetic field all around a wire like this have magnetic field lines pointing out of the page at locations above the wire and into the page at locations below the wire. So when I take wire number 1 and place it in the field of wire number 2, that's the reason that there's a force. In this case, we would say the force on wire number 1 is equal to the magnetic field created by wire number 2 multiplied by the current in wire number 1 times the length of the wire. So once again, we would get force per unit length is equal to, okay, so the magnetic field created by wire number 2, if these wires are a distance apart labeled as r, would be mu naught times I number 2 over 2 pi r, and then I have to multiply that times I number 1. So you see, it's the same sort of argument. No matter which way we look at it, the force per unit length between parallel wires is equal to mu naught times the product of their two currents divided by 2 pi r. Well, that at least gives us the magnitude for the force per unit length, but what about the direction? When two wires have currents flowing in the same direction, do they attract or do they repel? Well, we can just go to the common notion that says opposites attract and like things repel each other. So I would assume that if the two currents I1 and I2 point in the same direction, then this amount of force per unit length represents a force of repulsion. Let's double check though and see if that's right. So let's just go with the notion we had in the first case, that I1 is the one that creates the magnetic field and I2 is the one that responds. So I number 2 is sitting in a magnetic field that points into the page due to this current that's flowing in wire number 1. And then we use the right-hand rule. If you put your thumb in the direction of current number 2, and then you put the fingers of your right hand into the page as indicated by these X's, then you end up finding that there's a force on this wire that points upward. So actually it turns out that wire number 1 attracts wire number 2 instead of repels it. Now let's just see if we agree that it would be attraction if we take the other look at this, that no, it's wire number 2 that's creating the magnetic field and wire number 1 is the one that feels the force. So one more time, let's draw this picture. That represents wire number 2 with this current I2 that's flowing to the right. So in the region above wire number 2, it creates magnetic field lines that are pointing out of the page, and along comes wire number 1 and sits in that magnetic field and has a current in it that flows to the right. So we point our thumb in the direction of the current in wire number 1, and then we take our fingers of our right hand and point them out of the page as indicated by these dots, And so I think you'd agree that your palm is facing this way, and it says that wire number 1 is attracted to wire number 2. So when it comes to parallel wires, currents in the same direction, attract. So does that mean current in opposite direction has to repel? Let's leave that as a question for now and make an investigation on that. Let's say we've got wire number 1 with the current flowing to the right, and this time we have a wire number 2 with current flowing to the left. So which way do you want to think of this? Is current number 1 creating the field and current number 2 responding? Let's try that approach. So we need to determine is what's the direction of the magnetic field in the vicinity of wire number 2 if that field was created by the current in wire number 1. So that means the magnetic field, we'll call it B subscript 1, the magnetic field that was made by the current in wire number 1 is a magnetic field that points into the page in the location of wire number 2. But the current in wire number 2 is flowing to the left, so we point our thumb to the left, we point our fingers into the page, and we find that the force on wire number 2 points downward. Alternatively, we could have said, no, it's the current in wire number 2 that's making the magnetic field. So that would be a magnetic field, what would it be? Once again, I'd draw a bunch of X's, right? The magnetic field due to this current in the location of wire number 1, based on the right-hand rule, would point into the page. So if I have a current that flows to the right, okay, point your thumb to the right, point your fingers into the page, and you find that the force points this way. So the force on wire number 2 is downward, the force on wire number 1 is upward, so yes, indeed, they are repelling one another.